In the last video, we were talking about pie charts, and before we leave that subject, let me just say a little bit more about them. They are pretty common, pretty popular, but not everybody likes them. I found an article online that claims that the pie chart is easily the worst way to convey information ever developed in the history of data visualization. So the guy who wrote this article is not a fan. And I'm not sure I totally agree with him, but I will give you a link to this article in Canvas in case you want to read it and decide for yourself and see why he thinks pie charts are not such a good idea. But I will say that there are some bad pie charts out there. For example, let me get back to it. This infamous example of a pie chart appeared on Fox News back in 2009, I think it was. It was shortly after the 2008 presidential election, which was when Barack Obama was elected for his first term. And they asked their viewers who they would support as the Republican candidate for the 2012 presidential election. It turned out to be Mitt Romney that year, but back in 2009, they were asking people who of various possible candidates they would support or be in favor of as the Republican presidential candidate for 2012. And they made this graph to show the results. Some people would back Sarah Palin, some would back Mick Huckabee, some would back Mitt Romney. And do you see what's wrong with this picture? Now, each of these percents is more than 50%, but it doesn't take up more than half of the pie chart. And when you add them all together, they add up to way more than 100%, which is not the way a pie chart is supposed to work. And the problem here is that these categories are overlapping. In other words, one person could say they support more than one candidate. So if you were fine with all three of these people, you would support any one of them. You got counted in all three categories. But that's not the way a pie chart is supposed to work. It's supposed to show what percentage of some whole thing, some total, falls into each of several non-overlapping categories. Okay, so now we're going to talk about the last main graph we'll look at is what's called a stem and leaf plot. And stem and leaf plots are sort of a cross between a list of numbers and a graph, like a histogram made out of numbers instead of bars. So instead of just like a solid bar that stretches out for each class, you've got a row of digits that show you how many of all your data values are in the 60s, how many are in the 70s, how many are in the 80s, and so on. And the idea is that this is something that you can easily do when you have a set of data values, not too many, but maybe just a couple dozen numbers, and you want to get some idea of how they're organized, how they're distributed, what kinds of numbers you have, how many numbers you have in the 60s and 70s and 80s and so forth. So this is supposed to be something that you can easily do by hand. Here's another example. And it's called a stem and leaf plot because you're supposed to think of this as the numbers are leaves growing off of a stem. So the stem represents the first digit of each number, and then the leaf represents the second digit. So in this example that we're looking at right here, see here this stem of 7, has a 3 and a 2 and a 6 and a 9 and a 7 and a 9 growing off of it. So that means that in this set of data values, there were 6 numbers that were somewhere in the 70s. There was a 73 and a 72 and a 76 and a 79 and a 77 and another 79. So this 9 right here, growing off of the stem of 7, represents the number 79. So looking at this, you can see right away, okay, there were lots of numbers up here in the 90s, lots of numbers down here in the single digits and in the teens, not as many in the middle of the range, like in the 40s and 50s. So to actually draw a stem and leaf plot, if you have an easy way of doing it, it might make things easier if you start by arranging your data in order. You don't have to. And again, it might make things easier if you separate them according to their first digit or digits, although you don't absolutely have to explicitly write that out before you start making your plot. But what you do need to do is make a column for the stems, the first digits, and then list the leaves in order after each stem. Write all the leaves the same size so they line up. And I have seen them with the smallest numbers at the bottom and the biggest numbers at the top, so going up like that. And then I've also seen them the other way, with the smallest numbers at the top, so going down. So either way is fine. I've seen it both ways. So let's try doing this. Draw a stem and leaf plot for the following set of test scores. Here's a bunch of scores that people got on a test. Let's arrange that using a stem and leaf plot. So I'll notice right away that some of these numbers are in the 70s. There's 70-something. There's a 90-something. There's 80-something. There's a number in the 60s. If we did want to sort them in order before we started to draw our stem and leaf plot, we could do that, and here's what it would look like. Might make it a little easier to see exactly what we're dealing with, but we don't have to. But here, I told you could go up or down, and here I just put the smallest number at the top and the biggest number at the bottom. So we've got room for the numbers in the 60s and the 70s and the 80s and the 90s. So there's our stem. And now we're ready to start tacking on the leaves. The first number on the list, before I sorted it, was 73. So growing off the 7, we're going to have a 3. Then growing off the 9, we're going to have a 4. Do you see what I'm going to do next? There's an 81, so what am I going to do with that? Yeah, I'm going to put a 1 after the 8. Then we have an 82, so that goes there. A 96, a 77, and so on. So when we're all done placing all the numbers, here's what it looks like. And you can see right away that the biggest category, the longest stretch of leaves, is the 80s. There were 5 numbers that were in the 80s, and that was more than there were in the 70s, which is more than the number of scores we had in the 90s. There was just 1 in the 60s. Now notice that they do kind of line up. The first leaves line up, the second leaves line up, the third leaves line up, and so on. And I've made all my digits the same size. That's important. If I didn't do that, if I didn't space them evenly, then it wouldn't be easy to tell that, yeah, there are more 80s than 70s. So you don't want to put different sized spaces. You want to line them up so that the first digits are all above one another and the second leaves are all above one another and so on. And you don't want to use a different size font. I mean, look at what's bad about this. The row of leaves growing off the 7 stretches out farther than the row of leaves stretching off the 8. Here, to make it more obvious why this was wrong, I changed them all to 81s. So imagine all of these were 81s, but there were 5 of them. That's still more numbers in the 80s than there are in the 70s. So this really should go out past the 70s. So you want to make sure all of your leaves are the same size as each other and they line up consistently. Okay, I'm going to end this section with an example of a bad graph. So in this example, pretend you go bowling with a couple of your buddies, you and Bob and Ed, and you end up with the high score. You win your game of bowling. You beat Bob and Ed, and you're feeling really good about that. So you go home, you fire up your computer, you decide to make a graph showing the scores that you three got. And then you take it to your buddies and say, hey, look at how we did at bowling last night. Here's me and here's you, Bob. And oh, look at you down here. Hey, Ed, look at me compared with you. Ha ha. Can you see something a little bit maybe misleading about this graph? Look how much taller this bar is compared to the other two, especially this one. But look at what scores they represent. You got 137, Bob got 136, Ed got 134. Those really aren't all that different. And the reason they look so different is that when you made your graph, you started at 132. And so these bars aren't showing the whole picture. They're just showing like how far above 132 each score was. So if we had started at 0, here's what it would look like. Here's you, here's Bob, here's Ed. And if you look really closely, you can still tell that your score is higher than the other two, but not by very much in the grand scheme of things. That's something to watch out for. If the scale of a graph does not start at 0, it can make the differences between the different values look a lot bigger than they really are.